What I'd like to do is take you through the presentation on our jet inline cleaning family. So we'll talk about the NanoJet, the MicroJet, and the HydroJet. I'll be focusing a little more on the HydroJet. But the same thing, the same technologies apply to all of the family of jet inline cleaners that AAT has. So if you look at the diagram here of the three different cleaners, you can see the HydroJet, the MicroJet, and the NanoJet have similar sections, and this just traces those sections to show you where the pre-wash, the wash, the chem iso, the power rinse, final rinse, and the dryer, of course, and the sound abatement sections would be in these cleaners relative to each other. And of course, the NanoJet being smaller is just going to have smaller sections in general, and the speed would be smaller, and the belt is smaller. In the MicroJet, you get a medium speed belt of somewhere around 1 or 2 feet per minute generally, up to 3 feet in some cases, like at Rockwell. And the overall length has grown to 13 feet. And then in the HydroJet, that's our biggest machine, basically it's just under 17 feet. And those sections are expanded so we can get faster speeds. The belt's wider, 24 inches, versus the 18 for the MicroJet and the 12 for the NanoJet. And, you know, the way we developed these, we developed the HydroJet first in 1998. And then a few years later, we learned a few things in building it and shrunk it down to the MicroJet. And then, of course, continued to learn things. And then in 2013 came out with the NanoJet, which is the world's smallest inline cleaner that uses chemistry. So I'm going to focus a little bit more on the HydroJet right now, just thinking that, you know, that you're looking at the HydroJet or the MicroJet, but the same things, we have the data on the other machines as well. So one of the things right off the bat you're going to see on all of our machines is that it's going to have a small footprint. We have the smallest footprint for belt size in the industry. The recirculated power PED wash is unique to our machines as well. And we're going to talk a little bit more about what PED means, progressive energy dynamics, in just a few minutes. So I'm not going to talk about that just now. We can get up to temperatures of 150 degrees in that rinse. The final rinse module is closed loop, is a standard configuration. That means that you would not have to have a closed loop system feeding it. We can make it an open loop system if you have a DI system in your plant and choose to run an open loop configuration. One of the very special things about our machines is the jet dry isolation. So everybody else would use a air knife isolation. We're using jet dryer isolations. It doesn't actually dry the board, but it effectively strips the chemistry and puts it back into the wash. And then finally, one of the big differentiating points we have on our machines is the patented displacement dryer. Our philosophy in drying is you don't want to evaporate any water on the surface of the board, because even DI water has some contaminants left in it. Even if it just absorbed the carbon dioxide out of the atmosphere, it could possibly leave a water spot if it evaporated. Certainly contaminated water would as well. So our approach in drying is to completely displace the water by blowing it off of the board and not drying it on the board. A few things about the Austin American technology machines that really stand out. We have the highest cleaning performance, the coherent jets, and the progressive energy dynamics I mentioned previously really give us the best energy for cleaning and best getting under parts. We're going to see a film in just a few minutes about how that works. So it's going to give you your highest clean performance. But also, because of that, going to give you your highest throughput. Not only do we have good cleaning, but we also have excellent rinsing and the best dryer out in the market today that gives you the highest throughput. And the cost of ownership is also the lowest. Not only do we have excellent isolation, chemistry control, DI control, but because the machine runs faster than the competition, you actually run it fewer hours. So the overall result is it costs you less to have an Austin American machine than the competition. And finally, the closed-loop technology. We have been pioneers in the closed-loop technology. All of our machines, our batch cleaners, our conformal coat cleaners, our stencil cleaners, and our inline cleaners all are closed-looped and offer a configuration where nothing goes to drain. That saves the environment and saves you money. So looking at the HydroJet cross-section, I just wanted to point out the sections that we have here. So in the initial section is the isolation section for the onload. Basically, it's where we used to put the pre-wash, but we have moved the pre-wash inside of the wash to save chemistry, and we found that to be a very effective design change. In the wash, you have essentially 5 spray bars in the MicroJet and the HydroJet configuration, and those 5 spray bars are impinging with coherent jets. We can vector the jets to give vectoring underneath the parts. It is the best way to get underneath parts with these jets. Following the wash, we come out into the isolation section, where immediately we strip the chemistry off and return it back into the wash tank. That strips off 90 to 99% of the chemistry, and there is some optional stuff that we can add into the isolation section that would provide additional isolation. That would be a wet ISO bar and another topside dry ISO bar. That generally would go to drain if we add those options. In the power rinse section, in the HydroJet, it would come standard with 3 spray bars, and you could add an additional 2 spray bars in the HydroJet. In the MicroJet configuration, you come with 1 spray bar, which can be extended to 3 spray bars. And those spray bars, again, are the coherent jets and give you very good penetration under parts to get the chemistry out, any chemistry that might reside in 1 mil gaps or in connectors and things like that. So very good. And that chemistry would be pulled out in the closed loop system that is recirculated back to the DI and the carbon tanks. And then finally, the final rinse comes directly from the DI tank. That gives you your purest water, and it is monitored and for purity and can be alarmed if it does not meet the purity levels that we want it to have. And then in the very final section, that is our patented mock dryer. And again, we are using jets, not air knives, and we'll talk about that in just a little bit more detail in a second and show you how that works. But this is the overall diagram for a HydroJet, similar to the MicroJet and similar to the sections that we would see in the NanoJet. So talk a little bit about the progressive energy dynamics now. And in designing the machines in the very beginning, we did not have progressive energy dynamics, I will say. We had the same energy in all sections. And what we found out through our testing is that, especially on no clean fluxes or very highly heated rosin fluxes and things like that, we needed to have, we're wasting energy essentially in the beginning. So when we get into the first jet, the wash number 1, if we had too much energy, we were just bouncing off the hard flux. And what we found is we didn't need a lot of energy in wash 1, the first bar, or the first section. What we needed there was just enough flow to bring the flux to temperature and to wet the flux with the chemistry so that we begin the softening process. And so we don't need a lot of energy in wash step number 1. When we get to step number 2, we want a medium amount of energy to come in, and we want that to begin to create flow underneath the parts. Now that we have a softened flux, we can get the flow established. And then in the wash step 3, we're going to come with high energy. We're going to begin what we call eroding the flux at this point, because we've got it nice and soft, and we want to begin eroding the flux underneath the parts. That's a very rapid cleaning operation versus dissolving the flux residues. And I'm going to show you a film in a minute that shows you how fast that really can be. And then in the wash 4, we're going to hit it with the highest energy jets. That's where we're really going to just knock it out and get rid of it. And that's very rapid, and we're going to look at that in just a second. So that's how the progressive energy works. We use various amounts of energy at various stages. The appropriate stage, we use the highest energy, and in the beginning stages, we use lower energy. That energy level is determined by our hole spacings, by our nozzle spacings, and by the diameter and the flow that comes out of those nozzles. Okay, so what I'm going to do now is I'm going to show you a film that shows a simulated BGA, which is made out of glass, and the substrate is made out of glass, and we're going to pass it through that progressive energy wash that I showed you just a minute ago. So I'll go ahead and start that now, and you can watch it run. So as you can see in the film, we've got the spray started, and the spray is spraying on the coupon. The coupon is passing through the lower energy sections, and we're beginning to get some flow established. As we get into the higher energy sections, you're going to see the erosion occurring. You're going to see that rapid removal of the flux, and the complete cleaning operation occurs in just a few seconds. All right, well, based on that video, you can see that the cleaning is very rapid in the progressive energy cleaning system. And what that really gives us when we look at inline cleaners versus batch cleaners, we can see that we can clean a lot tighter gaps. And by cleaning, I mean completely remove the flux. In batch cleaners, we can generally clean down to 2 to 5 mil gaps. We start having a lot of difficulty below that. But in the inline cleaning process, we can get down, because of the energy, down to 1 mil gaps. So we can do things like flip chips, QFNs, some of the capacitors and resistors, which are more difficult in the batch cleaner. So talk a little bit about the displacement drying now, and what we're looking at in displacement drying is getting rid of the evaporative drying, and basically going to what we call displacement drying. So most of the other dryers out there use a combination of both the displacement from the air knife and then evaporative drying using heaters or just convective heat. So what we're doing is we're not using the heaters, we're not using convective heat. We do get some heating in the turbine, so we're running at about 100 to 120 degrees Fahrenheit, but we're actually going to be blowing off the water. So in evaporative, we're going to heat it up and evaporate it, and of course when we do that, that leaves residues behind. Our approach is to use a mechanical approach, come in and push the water off, and that is the approach that we take. In doing that, it takes, in theory, about 200,000 times more energy to evaporate the water than it does to push the water off of the board. This is really shown and illustrated well in this graph right here. That is a test that we performed comparing a air knife, which is used by traditionally on all the other cleaners, versus the air jet that we have developed and patented. So this is a single pass of a dense motherboard-like board, where we are looking at the amount of water remaining on the assembly over here in grams of water per meter squared, and then on the x-axis we're looking at the conveyor speed. And if you look at the blue line here, you can see that for the air knife we have a lot of water left after a single air knife pass, so we have to make multiple air knife passes and probably use heat in order to get this water off. So we're leaving, even at 1 foot a minute, we're leaving 20 grams of water per square meter on that board. With the air jet, at that same 1 foot per minute, we're leaving less than 1 gram per meter squared. And even at the higher speeds of 5 feet a minute, we're only leaving about less than 5 grams per meter square of water on the circuit board. And so you can see in this graph that the air jet is much more effective than the air knife is. So in just looking at this in computer modeling, when we looked at the computer model for the air knife over a 3-inch distance, we found that the high velocity, 200 mile per hour velocity indicated by the red portion of that jet, breaks up within an inch and quickly slows down to less than 50 linear feet per minute, or per second, excuse me, compared to the air jet, which over that same 3-inch distance holds together the entire distance and impinges down on the board with that full energy to the board. that is the energy needed to push the fluid out from underneath those parts. The air knife at 3 inches just does not have the energy or the velocity to clean underneath or to remove the water underneath the devices, so it has to heat the board and dry that water. And looking at the air jet in this photo here, you can see that the water is literally jumping off the surface of the board as it comes through, and that is what we mean by displacement drying. So I'm just going to go over a few of the maintenance benefits that we have in the machine at this point. Of course, we've talked about the compact design. That really minimizes your floor space, makes it easy to install, lowers your cost of operation for the machine. And in terms of the machine design from a maintenance standpoint, I wanted to point out in this second photo here that we have a vertical mount pump. We don't use the traditional lay it down on the ground pumps. The advantages of that is that one, it doesn't take up much space. It's right on top of the tank. And the major maintenance advantage we get out of that is that you don't have any seals in this pump. The pump is down in the fluid below the pump, and because it's in the fluid, it does not require any seals. So it just pulls the fluid in and takes it out through the distribution manifold, which you can see is in the third photo here, you can see is very well and easy to plumbed and easy to maintain. It has flow sensors and what have you. And these two screens down in the lower tank are used to remove particulate that might fall into the tank as well and protect the pump. It's a very easy to maintain, easy to use system, and that's one of the reasons that we have advantages both in footprint and in maintenance, is the way that we designed the pumps for the wash and the rinse sections, I might point out. So some other things that we look at, we have easy to upgrade spray bars. You know, if you have a need for a different spray bar set, you know, maybe you don't need the high energy, maybe you need fan jets, those are easy to change out. The HEPA filter on the dryer, we use a single blower for the dryer. It has a built-in HEPA filter. It's conveniently located right behind the door, easy to change the filter, easy to access the blower and to change the belt on the blower if you need to do that. No problem doing that. It also has a color touchscreen interface, which simplifies the use. It has alarms on the screen that would keep you posted on the status of the machine. It has icons that will show you if there's any alarms and keep you posted on the machine status. As far as other features that we have in the machine, I mentioned the screens. This is just a better shot of the screen showing you have dual screens going into the pump cavity that keep any tape dots, you know, or anything that would fall into through the primary screens in the wash tank, and we keep them out of the pump. We have quick disconnect plumbing so that it's toolless. You can do this, you can maintain this without any tools, and it's very simple and chemically resistant. Removable front panels allow you easy access to the heaters and the heater control box, making your maintenance operations and checks very easy to perform. Yeah. We also have a lot of these machines out in the field. I just wanted to give you, here's a couple of the customers that we have that have multiple inlines from us, and they are available for reference if you wanted to talk to them about their cleaners and how we've dealt with them. In summary, the AAT Jet Inline series has superior cleaning performance because we have better cleaning jets, and we have designed them through computer simulations and through actual testing where we've taken the transparent assemblies that you saw on the film, and we've run hundreds of tests to determine the best spray configurations that clean the boards fastest. So you get the highest throughput in our machines, not only because of the cleaning, also because of the better drying, and you get lower cost in terms of operating costs because we are better at stripping the chemistry out and keeping the closed loop system maintained properly. The inlines are designed to maximize your performance and your lower operating cost I think you've seen that clearly in the presentation. And we've been doing this for over 30 years. And so we have a lot of experience, so we can help your team out. We can be the third party that when you need that expertise, call on us, and we've probably seen it before. So we've been doing that for 30 years, and we're ready to keep doing it for another 30 years. Look forward to running the test with you guys and showing you these advantages so that you can realize these advantages for your company. Appreciate your attention.